Okay, thanks a lot, Veronica. It's a pleasure to be lecturing at TASI. Please interrupt me as much as you can and slow me down. Okay, so the subject of my talks will be on the recent progress on the information paradox, in which I'm going to try to convince you that it's a paradox no more. But nevertheless, it remains a sort of a hard problem, or at least some aspects of it remain a hard problem. Now, I can say things like that because I know that I'm not recorded. Actually, wait, there was a recording thing, right? I know, I'm kidding. Okay, while I'm in the middle of corrupting the minds of the youth, let me begin with something that some people have been calling the central dogma, or the central dogma of black hole physics, which states that, at least as seen from the outside, a black hole behaves like a quantum system with a number of degrees of freedom, which goes as the area of the horizon over 4g Newton, and that it evolves unitarily under time evolution. Okay, what this means that so long as you're interacting with a black hole purely from the outside, you're justified in replacing the black hole with some part of its sort of exterior region with a ordinary quantum system. You would not be able to tell the difference if you're just interacting with it just from the outside. And my lectures will be about justifying this replacement, at least from the perspective of some quantum information aspects. The upshot will be that that in the theory defined by the so-called gravitational path integral, this idea will hold, that the gravity path integral is consistent with the central dogma. Okay, so that's the introduction. Now, part of being a theoretical physicist is the search for the simplest possible toy model to study your question, but without compromising on the physics that you want to analyze. For us, that's going to be studying a two-dimensional black hole in perhaps the simplest theory of quantum gravity, namely that of Jakob-Teitelbaum gravity coupled to matter. So the model is defined by the action that I have here. So it's a dilaton gravity theory, which means that well, I'm going to call these two fields, the dilaton and gravity, collectively as the gravitational degrees of freedom. And they're going to be coupled to matter, which I'm going to take as some conformal field theory. The total action has it has these two terms. The first term is the infamous JT action involving, as I just said, the 2D metric and dilaton on some manifold M2. Okay, some two-dimensional manifold M2 right here. Let me see what I want to say about this. Yes, so the first term in the JT action is topological. And can be evaluated using the Gauss-Bonnet theorem to be equal to 2 pi times the Euler character of M2. Okay, we're only going to consider orientable surfaces for which the for which the Euler character is just 2 minus 2g, g is the genus, minus b, which is the number of boundaries. You should, even though for the first 3 talks, we're only going to focus on the case where M2 has trivial topology, where by that I mean it's like a disk. You should keep in mind that in the gravity path integral, well, it's gravity, so you have to consider all possible surfaces, and so you would get things like a disk. You might get a disk with a handle, and 2 handles, and so on and so forth. But I'm getting ahead of myself with this. Okay. The second piece of the action, let me use the pointer, this guy here, is sort of where all the action is. Sorry for the pun. And it describes the interaction between the dilaton and, oops, let me use a different color, between the dilaton and the metric. Okay, so this is the dilaton. And R here is a function of the metric, just the usual Ricci scalar. And this second piece also breaks up into 2 terms, one which is a bulk term and one which is a boundary term, required to ensure a well-defined variational principle. The matter, okay, so that's the gravity action. The matter action, which is just this term here, it's going to be a general CFT defined on the background metric G. So the CFT only couples directly to the metric, does not couple directly to the dilaton. That's going to be important. This theory also comes with some boundary conditions. We want to consider solutions that are asymptotically ADS. And so the statement is going to be that the GUU component of the metric goes as 1 over epsilon squared. U is like, it's the boundary proper time, while epsilon is, you can think of it as the holographic radial direction that's perpendicular to the boundary. Okay, so that's for the metric. We also impose some boundary conditions on the dilaton, that it goes as, it has some boundary value, phi b, which goes as phi r over epsilon, where phi r is sometimes called the renormalized value of the dilaton. Okay. The really nice thing about this theory is that the metric localizes to ADS2 because the path integral over phi can be done exactly, and it can be, if you consider the integral along a contour which is parallel to the imaginary phi axis, you can convince yourself that this integral is essentially just a delta function. This imposes delta r plus 2. Okay, so r is equal to minus 2, which is just the ADS2 space. Furthermore, we can get Einstein's equations in this theory if we vary with respect to the metric. If you do that, then you get an equation which couples the dilaton to the expectation value of the stress tensor of the matter CFT on ADS2. This box here is just some differential operator which depends on ADS2. So maybe I should, it depends on the ADS2 metric. Okay, so that's the model. Next, let's talk about solutions to this model. Are there any questions? Excellent. Okay, So for the solutions, we're going to consider vacuum solutions to this theory, which means that the stress tensor is 0. And it just so happens that all the vacuum solutions of this theory are eternal black holes. Let me give you, write down these solutions in 2 different coordinate systems. The one on the left, I'm going to call this coordinate system the black hole exterior, or the Rindler coordinate system, where time in this coordinates, or maybe I should just read out what the coordinates is. So, well, u is the time variable, which runs like this up here, and you can define it to also go down there. This metric has a killing symmetry, which is this time evolution that I just drew, or the boost symmetry. So this is u, and sigma is orthogonal to u. So sigma just grows in this direction. This point here is sigma equals infinity, and the absolute asymptotic boundary here is sigma equals 0. While the physical boundary, the thing that on the previous slide was labeled as boundary of M2, that's this thing here, at sigma equals epsilon. Okay, you can convince yourself that if you put sigma equals epsilon here, take epsilon to 0, you'll find that the pullback of the metric is just 1/epsilon squared, like which is the boundary condition that we imposed. The dilaton also has static form. That's this thing here. It just goes as 1/10 hyperbolic, and it has a finite value at the bifurcation surface. Okay. On the right, I have the same solution, but yes.
Hi. Just the Rindler coordinates that you wrote down cover only one wedge of that geometry, right?
Sorry, I couldn't hear you. Can you say it again?
Those coordinates that you wrote down, the Rindler coordinates, those cover only one wedge of the geometry you have, right?
Perfect. Yes, exactly. So as written, these coordinates cover one wedge. However, they can be easily extended to all the other wedges, just by a series of analytic continuations.
Thanks.
Yeah. Oh, something I forgot to emphasize is that you can choose to work with null coordinates, these y plus and y minus, which are defined with respect to u and sigma in this fashion. Y plus minus is u plus minus sigma. Okay, then there are.
Before you go on, can I ask a question?
Of course.
So when you integrated out the phi field, you said that the metric localizes to ADS2.
Mm-hmm.
Where does this metric come about then, if we've already localized to ADS2? Is this just a portion of ADS2, or what's going on?
This metric is the metric of is ADS2 in some coordinate system.
Okay. Like, so that's all that's going on. It seems like there's more going on here.
This is not the most convenient coordinate system. The Poincare coordinates are more convenient, and there it's clear that it's ADS2, right? You're probably familiar with this form of ADS2.
Yeah, I'm also a bit confused about these diagrams. It doesn't look like the traditional diagram of ADS2. Like, what are these horizons doing? Is this just supposed to be the ADS cylinder? Like, I don't know what these. Yeah, it doesn't look like the traditional picture of an ADS cylinder. Okay,
good question. The first statement is that we are in 2 dimensions. Okay, so we don't have a cylinder.
Okay, yeah.
We just have a strip.
Yeah.
ADS space in 2 dimensions, like let's just ignore JT gravity, ignore everything I said on the previous slide. ADS2 in 2 dimensions is just an infinite strip. Okay, and you can write this. Metric. You can consider coordinates that cover different patches of the strip. The black hole exterior coordinates, they cover a patch that looks like this. Okay. So far, I didn't motivate it. So I'm just telling you what you're allowed to do. You can also choose to consider coordinates which cover a Poincaré patch of ADS2. Okay. There are blue coordinates. The coordinates that cover the entire blue strip are called global coordinates, which I am not going to use. Okay. So far, I'm just telling you different ways of slicing ADS2. Are we okay with that point?
Yes.
Okay. The next thing about JT gravity, and now something which is a bit more special to JT gravity, is that I'm going to go back a slide. We had these boundary conditions here. This is meant to there's a sense in which you have some with these boundary conditions, it tells you where the physical boundary is. Like there's a coordinate boundary of ADS2, and there's something which I will call the physical boundary of ADS2. Okay, that's where if you are familiar with ADS-CFD, the physical boundary is where the holographic dual would live. And the way you define that location is by imposing these conditions that I have over here. And what you find is that when you do this, these locations are at least for the eternal black hole with non-zero temperature, it looks like it has two. You're allowed two of these boundaries which can sort of satisfy these boundary conditions. Did that make sense?
I have to think about it, but that was helpful. Thanks.
Okay. So far, all you need to know for now is that we're just looking at a class of solutions of JT gravity, which have this metric and this dilaton. Okay. There was another question?
Yeah, just to follow up on what you said a moment ago about the physical boundary. What you mean is that the value of those fields with the boundary conditions basically define the value of the fields on the conformal boundary, and so you mean that the conformal boundary is the physical boundary? Is that what you meant, or something different?
If by conformal boundary you mean this guy? Is that what you meant by the conformal boundary?
Yes. So the boundary that has the metric given by the DS metric rescaled by conformal factor.
Yes. Then yes, I agree with your statement.
Okay, thank you.
Okay.
Sorry, another quick question related to that.
Yeah, please.
I was wondering if you're adding matter, like the CFT on the background metric, what are the boundary conditions you impose on the matter? Are they supposed to be imposed on the level set of the dilaton, or? Good.
So so far, so far you should think, should imagine that the matter also has Dirichlet conditions on these boundaries. Okay. For now, but that's going to change soon. Okay.
Thanks.
Yeah. Okay. So let me rush through this part. So you can also work in Poincare coordinates where slices of constant z look something like this, and time runs along these slices. Okay? And so this is the famous ADS form, Poincare ADS coordinates, and you can also choose to work in null coordinates as well. And so the metric is much simpler than the metric of the black hole exterior coordinates, but the dilaton looks more complicated. The killing symmetry of the space-time is not apparent in these Poincare coordinates. The last thing I wanted to say about this is that there's a coordinate transformation that goes between these two coordinates, which is just this simple transformation here. Okay, let me move on. So that was setup. Now let me give you some more setup. What I'm going to do is that I'm going to include what I'm calling, oops, this is not supposed to be eternal, it's supposed to be external. External flat space CFTs, which I'm going to call paths, which I'm going to join to my ADS2 space along these boundaries. Okay. So I have two paths, and they're joined on partial N2 at sigma equals epsilon. These CFTs, they do not have dynamical gravity. Metric is fixed to be this value. I chose this value to make the metric continuous from the bulk from the ADS2 spacetime to the flat spacetime. And note that epsilon is small. That's just keep that in the back of your mind. What this identification does for this flat metric is that the bath time gets matched with the external black hole time near the boundary. So if you recall, the time outside, it flowed this way, so we have slices like this. And now I'm just extending this time into the bath region. So the bath time is identified with the time as measured outside the black hole.
I have a question.
Yes.
So the blue line, is that allowed to wave around, or is it just fixed?
Yes, it is allowed to, it is allowed to move around. In fact, that's the only quote unquote gravitational degree of freedom in JT gravity. But thankfully, so I could have given another version of this talk where I discuss the dynamics of this quote unquote boundary particle, but for my purposes, I'm never ever going to need to do that. Like I'm never going to need to make this particle fluctuate and move around and so on. I'm always going to consider this fixed static solution. But the answer to your question again is yes.
Thank you.
Yeah. Okay. So as in the way that I just described it, the bath time gets identified with the external black hole time near the boundary. Now let's talk about boundary conditions. On M2 or boundary of M2, again, I want to continue to have Dirichlet for the metric and dilaton, basically because, well, we said that the metric is fixed in the bath, and second, the bath doesn't have a dilaton. Okay, so we want the dilaton to be fixed. We don't want it to go into the bath. Second, for the matter, we want Neumann or transparent boundary conditions. So if you have an excitation here, it can fall in smoothly into the bulk, and if you have an excitation here, it can go smoothly outside. Now, I claim that this sort of, you might ask, why am I motivated to consider such a weird setup? Well, I claim that you should think of this as a toy model for the standard maximally extended Schwarzschild black hole in asymptotically flat space in any dimension. Everything I'm going to say about this toy model, about this hybrid black hole. So sometimes I can use that term, hybrid black hole, applies equally well to Schwarzschild in any number of dimensions, to maximally extended Schwarzschild. Okay, if there are no questions about that, I'm going to talk about some thermodynamics of black holes.
Wait, sorry, I have a quick question.
Right.
Can you just say again where the black hole is here? I must have missed that.
Oh, okay. That's sort of a sign, I don't know, of my age or something. I don't know. But I'm thinking of black hole in a sort of more generalized sense. I guess your objection is what shouldn't I be calling this a wormhole? I mean, yes, it is a wormhole, but a wormhole is just a two-sided black hole. So this is a black hole in the sense that you have an event horizon. Is that clear? Or
I think I missed that too. I think my question is more basic. Are you just talking about the Rindler horizon that you just see when you write down the Rindler coordinates?
No. Yes, it just so happens that the naive, stupid Rindler horizon is in this toy model is actually the event horizon of the black hole.
Okay.
So imagine you're an observer in the bath. You can choose to stay out here for all infinity, or you can choose, for example, to go in the bulk a little bit and then come back out.
Mm-hmm.
But suppose you go a bit too far in, you cross the horizon. That's it. You can't come back out. What happens that you go into this region where things are a bit confusing. This is a lot like, actually, maybe I should have drawn a different black hole. This is a lot like Rising-Nordstrom. Right, so in Rising-Nordstrom black hole, you have something like this. So even though this is not entirely precise, but even in the toy model, you can think of there being a singularity, a time-like singularity like that.
Hmm.
So in that sense, this is a black hole.
I see. Cool.
Okay.
Thank you.
Okay.
Excuse me, can I ask another
Yes.
question?
Yes.
You mentioned that this should generalize to higher dimensional black holes in flat space-time. And I want to know, doesn't it matter at all the fact that 2D gravity is not dynamical? Like the fact that in the higher dimensional black holes, you actually have back reaction providing gravitons and so on. Does that change the picture at all or not?
So you might have thought, like, this was sort of one of the reasons why a lot of people sort of ignored 2 dimensions. But I think people have sort of come around to understand that even that there are features of gravity independent of the things that you just described, which are sort of the key sort of features to make progress on the information paradox and so on. Well, to answer some questions. Sorry, let me see. Yeah, so again, just to summarize my position, that in 2-dimensional gravity does miss a lot of aspects of higher dimensions, but nevertheless, it continues to share aspects that are important and which will be key for this question that we're analyzing. That's the position. Okay, so let me move on now.
Related to the earlier question about why this is a black hole, so would we also think of this as a black hole if there wasn't, if we didn't include these bath CFTs?
Yes, so even without the bath, so if you completely ignore this, it still has the structure that I described. So you can be an outside observer here, you can choose to stay outside for all infinity, or you can choose to go in and then you would either crash into the singularity, or you would continue to the other asymptotic region in the future, right? So Rising Nostrum continues. So you would go in and you would come out the other future universe and so on. But I guess maybe I guess I should have drawn the ADS version of Rising Nostrum. Maybe that more clearly answers your question, and so on. Did that answer your question? Okay.
Yes, great, thank you.
Yeah.
Sorry, but wouldn't that make the event horizon observer dependent?
In what sense?
In the sense that, I mean, we can pick to put these null lines in and call it an event horizon everywhere that we want in the ADS strip.
No,
if you didn't have these.
Sorry to interrupt. I drew these horizons and the location of the singularity independent of talking about an observer, right?
So do we actually have these singularities in the solution
here
that you described in the? Oh, I see. Thank you.
Yeah. Well, we don't understand the physics in that region very well. Some people like to call it a singularity, other people don't. The dilaton goes to -infinity, but it's not quite clear that it's a singularity, but I think that's a bit too high level of a question.
Thank you.
Yeah. Okay, so now let me talk.
Just a quick question, sorry.
Yeah.
What would be the mass of these black holes?
We'll get to that, I think. Okay. Their mass is set by this parameter beta that I talked about. Okay, so now let's talk about thermodynamics. Okay. Let me see what I want to say here. Okay. Okay, so to study thermodynamics, one usually considers the partition function, which is in regular quantum theory, it's given by the trace of e to the minus beta tilde. Beta tilde here is some inverse temperature, which can be thought of, again, in a quantum theory as a Euclidean path integral on the circle. So Euclidean path integral on the circle, or just on your system with a periodic time direction. Maybe I should just write that, where tau goes to tau plus beta tilde. Now, Gibbons and Hawking proposed that you can study the statistical mechanics of gravity by using the Euclidean formulation of the gravity path integral, and then you specifically study that the thermodynamics of the black hole by plugging in or by evaluating the path integral on the Euclidean black hole solution. So you would write this as e to the minus I classical. By this I just mean you evaluate the path integral on the saddle point given by the Euclidean black hole. So you'd get something like this, e to the I classical times some z quantum. So z is the path integral, and you simply ignore this term. Okay, so if you do this, you can then define, you can use this to define a thermodynamic entropy or a thermal entropy of the black hole by using the standard formula for the entropy, which is 1 minus beta tilde d beta tilde of log z. And this thing, if we take this is simply 1 minus beta tilde d beta tilde by JT gravity on shell. By on shell, I just mean you plug in the Euclidean black hole action. Okay. I will go through this calculation very, very quickly. Are there any questions about this? Okay, so let's do this. So first, let's discuss what the Euclidean black hole is. What you do is, well, it's an analytic continuation of the Lorentzian black hole, where you take the time u to minus I tau. So if you do that on the solution, you would get this metric here. The only thing that changes is the sign of the time variable here. The procedure, I drew it in pictures. So here's the eternal black hole, maximally extended. Notice that it's static, and it has Z2 symmetry about this red line that I drew. What this means is that you can continue the time variable to Euclidean. You can continue it in this fashion, and then the space-time will look like this region here. It will look like a disk or a half a disk. You can then choose to continue it also in the future, and you'd get the full disk. And this picture you might be familiar with if you sort of bend it to look something like this. You might know this as a Euclidean cigar. Okay. The event horizon, which was here in the center, is the tip of the cigar. So, okay, now let me emphasize that the time here is periodic in beta tilde. Now, it turns out that the space-time is actually singular for general beta and beta tilde. And you can see that by expanding this metric near the tip. And I won't go through the steps, through all the steps. I'll just show you what the last line looks like. By a suitable change of coordinates, you can write this as dr squared plus r squared times d of 2 pi over beta times tau squared. So if you call all of this tau hat, you find that near the tip, you have flat space, but where the angular direction has periodicity, tau goes to tau hat plus 2 pi beta tilde over beta. Okay, so this means you have a conical singularity if beta is not equal to beta tilde. Okay. So this shows that the solution you should consider, given this boundary condition that tau goes to tau plus beta tilde, is a black hole whose periodicity in Euclidean space is given by beta tilde, which sort of suggests that that this beta variable here should be thought of as a temperature once you set it equal to beta tilde. So so this is smooth if and only if, sorry, that's 2 F's, not 2 I's. If and only if beta is equal to beta tilde. So this tells you this parameter is like temperature. Okay, and the dilaton doesn't depend on U, so it doesn't change. Okay, now I'm going to evaluate the.
Can I ask a question?
Yes.
Do we ever consider the temperature being 0 here?
I mean, you could. So you can choose beta tilde to be minus infinity, sorry, not minus infinity, just infinity, you would get an extremal black hole. So an extremal black hole, it exists in JT gravity, and it looks something like this. It only has one side, like that. The black hole exterior coincides with the Poincare coordinates. So if you allow me to draw singularities, the spacetime will look like this. This is the exterior. And you can choose to, if you want, you can also put it back. But this is a temperature equals 0, beta equals infinity black hole. Okay. Now let's evaluate the action. Okay, so here's the action. So this is not going to be too hard to do. This term here is topological. We have the disk, so this is just 2 pi. Over here for this term, because the metric is ADS2, this term is 0. So this means that the only thing that survives is the boundary term. This for the second part. Then you get this. Let's just focus on this term. Oops. Focus on this guy. You should do this calculation at home. You can show that the K here is the extrinsic curvature of the boundary M2. That's this blue circle here. And you can compute it, and you find that it's equal to 4 pi squared over beta squared times 1/2 times epsilon squared. Okay. So K goes as 1 plus this. Since this doesn't depend on tau, this term here just evaluates to the proper length of the boundary curve, which is just going to be beta tilde divided by epsilon. Remember the boundary condition for the metric is that it went as 1 over epsilon squared, and tau had a periodicity of beta tilde. Putting everything together, all the epsilons cancel. I should have said that in the extrinsic curvature, there are corrections which go as higher powers of epsilon. So they would be subleading or go to 0 when epsilon goes to 0. You put everything together and you get this expression here. Then you take this and you plug it here to compute the thermal entropy. You take the derivatives and you get this expression. This second term here is simply phi, the solution of the dilaton, evaluated at the horizon or at the bifurcation surface. And let me see what I want to say here. This is precisely the Bekenstein-Hawking entropy of sort of the 2-dimensional black hole, but where the dilaton plays the role of the area. So this term, all of this is like the area of the event horizon. Okay, let me make some comments about this. So this result is, well, actually, did anybody have a question?
Yeah, can I ask a quick question? You said that
Yes.
the PR is the dilaton at the horizon, but isn't PR the value of the dilaton at the boundary?
Correct. Phi r is the dilaton at the boundary, but remember that the solution for phi is it's related to phi r. It's phi r times 2 pi over beta times 1 over tangent hyperbolic of, I think it was like 2 pi over beta times sigma, something like that. So if you take sigma very large, you take sigma to go to infinity, which is where the event horizon is, this term is just 1. And then this piece this piece is the same as this piece.
Perfect. Thank you.
Yeah. Okay, so the dilettante plays the role of the area. Any other questions? Okay, what I wanted to say here is that this result is nothing short of sorcery. In statistical mechanics, the thermodynamic entropy comes from counting the total number of microstates that correspond to a particular macrostate. So, and then you take the log of the number of microstates. So basically, the entropy is log of omega. Omega here is the multiplicity or the number of microstates. But gravity assigns the black hole a thermal entropy using a single classical solution without offering any information on the nature of these microstates. In fact, there's evidence that gravity can't know about the microstates, and you need a more fundamental theory, something like string theory, to tell you what they are. But nevertheless, gravity knows how many there should be. I mean, I was there for Ashok Sen's talks at the very beginning of this school, where he was counting these microstates using string theory and matching to the Bekenstein-Hawking answer in gravity. But it's mind-boggling why that works. And this sort of mysterious power of gravity is an open problem. And so why, or not why, but how? How does gravity know? It's an open problem, and I will assign it as homework with an open deadline. Okay.
Can I ask a quick question?
Do you have the answer to this question?
No, definitely not.
Okay.
Can I just ask, so the fact that you ended up getting the entropy that depended on phi at the horizon when you took sigma to zero, is that it? Oh, sorry, infinity, never mind. Is that like the attractor mechanism, or is it something different happening?
I have no idea.
Okay.
Sorry.
No, all good.
Okay. Okay, so that's this. Okay, let's now talk about the interpretation. If there are no questions about this, I can. The next thing I want to talk about was the interpretation of beta. Okay.
Can I
Yes.
ask a question? So so here you calculated the leading order contribution to the Bekenstein-Hawking entropy, right? You ignored the quantum corrections. So if you include that, then you'd have to include more and more different geometries. Isn't that somehow related to, I mean, at the leading level, you can determine the entropy using the classical solution, but if you want to go higher up, you need to include the quantum effects, right?
Well, correct. There are two notions of quantum effects. So when you compute Z, you can have a suppose we consider saddle point evaluating the path integral by saddle points. So we can write this as a sum over saddles. So I e to the I gi, and around each saddle there are fluctuations. Okay, so that's like my Z quantum that I had before. The statement is that, so if you, suppose you ignore the sum. So one notion of quantum corrections is the correction about each saddle. So the geometry is the same, but there are small fluctuations everywhere. Another notion is to say that there are different saddle points. some people describe this as a, I mean, it is a quantum thing, where you have different saddle points contributing. Actually, is that right? Maybe it's a terminology issue. But anyways, you can have different geometries contributing to the path integral. For example, I consider the disk, but there could also be the disk with a handle or with two handles, etc. This latter type will be important for our discussion, maybe in the third lecture and fourth. This discussion here, the effect of Z quantum will be important in the next lecture and the one after it. Or starting from the next lecture. Did that answer your question?
Yes, I was actually, the comment that I was trying to make was, if you want to sort of enumerate how many different saddle points you have, isn't that sort of similar to counting the microstates?
No. So all the calculations, all the counting that you guys learned about in Sen's talk was looking at a particular, if I understood correctly, actually, looking at a particular term in this sum, looking at the leading one. So zero. So let's get one. So you guys only looked at one of these terms. I don't think people understand, or maybe they do. But my suspicion is that people I don't think have extended the counting to these other possible geometries, quantum. But the full, like, it's yeah, the entire counting, the counting that Ashok was talking to you guys about, was trying to match the answer from just one of these guys. One solution plus quantum corrections. In fact, I'm not even sure how much of these quantum corrections are known. But I hope that answered the question.
Yes, it did. Thank you.
Yeah. Okay, next, let me talk about the interpretation of beta. To do that, we need to talk about the quantum state of the CFD. The first thing I will discuss is how to derive the stress tensor of the quantum state. So it's a fact about two-dimensional CFDs that you have holomorphic factorization. The stress tensor, by that I mean that the stress tensor breaks up into a purely left-moving and a purely right-moving pieces. And one can determine, the trick we're going to use to determine the stress tensor is its transformation due to the Weil anomaly. So basically just how the stress tensor transforms under changing coordinates or doing a Weil rescaling of the metric. Let me go through those in detail. So let's first discuss just applying a Weil transformation. Suppose you have a metric ds, just some metric g, which is related to some metric eta via some Weil rescaling, omega to the -2. Then what this conformal anomaly tells you is that the expectation value of the stress tensor in G is related to that in eta well, it's equal to that minus this contribution. C here is the central charge of the CFD. Okay, so that's how a Weil transformation, or that's how T transforms under a Weil transformation. While for a coordinate transformation, say the y is going to some w, which is a function of y. Again, I'm imagining this is a holomorphic transformation. The stress tensor transforms just in the usual way as a tensor transforms under coordinate transformations. So you just get something like this. You just get this extra factor. Now, if you do something like if you do both transformations, a coordinate plus a vile, then what I mean by this, first actually, let me define what I mean by doing a coordinate plus vile. So it means you start with the flat metric dy plus dy minus in this coordinate y, and you want to do a transformation that takes you to a new coordinate w as a function of y, but also the flat metric in w. Okay, where this flat metric in w is related to that of y via a vile rescaling. In fact, this is what we mean in CFT when we say conformal transformations. Remember, this confused me a lot as a grad student. The conformal transformation, like it's not just a coordinate transformation. It's a coordinate plus a vile transformation. Okay, it's an important point. And when you do that, the way the stress tensor transforms is, well, what you get is this guy here. You get a piece which looks like the ordinary transformation of just a tensor, but then you get this anomaly piece. In fact, this is the reason why the stress tensor in a 2D CFT is not, or rather, yeah, it's not a primary. It's often called a quasi-primary. Because only for coordinate transformations in which this term is zero, namely SL2 transformations or the Mobius transformations, yeah, unless you're doing those, the stress tensor would pick up this piece. Therefore, SL2, this is zero. Okay. So that's
sorry.
Go on.
Just a question. Could you define what's the bracket on that second term?
Good. I was hoping that Phil Saad talked about this. So this is the Schwarzian derivative.
Oh.
Fx is, I'm going to get this wrong, but let me try. It's f prime, double prime over f prime, prime minus maybe 1/2 f double prime over f prime squared, something like this. It's the Schwarzian derivative.
Thank you.
Welcome. Okay, so that's how this is just some machinery of how the stress tensor transforms and so on. Now let's apply it to the black hole case. So let's go back to our black hole and let's focus on the right black hole exterior. So that's this picture here. This is just part of the black hole spacetime. Remember that the metric here is ADS2, given by this, has a non-trivial warp factor. And flat space is just given by this guy. Let's imagine, actually, before we imagine, let me first ask you guys a question. Please just shout out the answer. What's the bulk stress tensor? P, y plus in the ADS2 metric. Anyone care to guess?
0.
Yep, it is 0. Remember, it's the black hole is a vacuum solution. Good. Now let's imagine applying or doing a vile transformation that removes this warp factor from the bulk part of the metric. So this means that in this entire diamond we have the Bath flat metric everywhere. If you do this vile transformation, you can go through the machinery on the previous slide, and you will get this answer. Okay. So the stress tensor after this Val transformation in the bulk region is just given by this very simple formula, C over 12 pi over beta squared. Now that is where the statement about transparent boundary condition is important. What this ensures for you is that any stress tensor, any right-moving stress tensor that starts here just goes out, and any left-moving stress tensor here would come from a region there, from the bath. Okay. What this means is that you should simply extend the extend this stress tensor into the bath region, and so this pins down the stress tensor of the bath to be this value, and this number turns out to be it's the value of the stress tensor that you expect in a CFT thermal state. In fact, like this is the only thing. Oops, no, what happened? Oh, there you go. This is the only thing you can write down that has the right dimensions. Just you can. This is fixed by dimensional analysis. Any questions about this?
So
Okay.
we're saying, oh, sorry, we're saying that there's a non-trivial stress tensor in the bath part, but there's not going to be any dynamical gravity there, right? So it's like there, but it's not going to do anything.
Exactly. All
Okay.
that's happening, like if you're in the bath, you're a bath person, you're just floating around there, you would notice that there's stress energy going into the ADS2 region, and there's also stress energy coming out of the ADS2 region. Okay. And we're going to explain why this happens in the last part of the talk. Any questions?
Can I ask a question?
Yes.
So we started with it, with the energy momentum in the bath being 0. Is that right? And then we're extending our energy momentum tensor to also be in the bath.
Sorry, can you restart your question? I didn't hear the first part.
Sure. Yeah. So we were, if I understood correctly, we're starting off under the assumption that there's 0 energy momentum in the bath, the CFT, and then we notice that you can do this wild transformation and make the ADS2 region look like an identical metric to the bath. And we see there's this, if we do this transformation, we get this non-zero energy momentum tensor. And hence we extend this to the bath region as well. Is that?
Your procedure was right, but your initial point was I think you mixed something up at the very beginning.
Okay.
But the procedure was right. The only thing, well, we're starting with a 0. We're starting with an eternal black hole in the bulk. So we know that the stress tensor is 0 in the ADS2 region. Then what we do is we can do a Val rescaling of the bulk region to remove the ADS2 metric. So now we just have a flat metric. Under this Val rescaling, we pick up some non-zero stress tensor. And then we are going to, when I said we have transparent boundary conditions, I want to interpret those transparent boundary conditions as saying that that the stress tensor of the bath is going to be equal to the stress tensor of the bulk after having done the Val rescaling.
Okay.
That's the idea.
Okay.
I have a question.
Yes.
So you're writing the stress energy tensor in sort of like these different space times. ADS2 we know has like sort of a cosmological constant, whereas flat space doesn't. So when you do this sort of rescaling, does that have something to do with this? Like in the bath region, you end up with a non-zero stress tensor because you're sort of coupling it to a space-time that has a cosmological constant.
In some sense, yes. like here, like even if you just focus on the bulk region, the fact that you picked up stress tensor, you picked up stress energy via this biotransformation, well, you can interpret this as coming from the fact that you've removed the warp factor, the ADS2 warp factor, which is like saying that you've removed the background cosmological constant, because it's the cosmological constant which makes the space-time ADS2. So roughly speaking, you have the right intuition, but I would say that the reason why the bath has any stress tensor at all is because of the transparent boundary conditions. This stress energy in the flat version of the bulk extends into the bath.
Okay, and just one more question. So right now we're not even considering like the CFT matter at all right now, are we?
We are. This stress tensor here is the stress energy tensor of the CFT.
Oh,
okay. of the matter CFT.
Okay.
Yeah. All right. I had one more thing I wanted to cover before the end of the talk, which is soon. So let me get through that.
You have about 5 minutes.
Wait, how do I have 5 minutes? It's 6:52 on my computer.
Oh, sorry. I take it back. Yes, you have 8 minutes.
Okay. Well, because of the stress you caused me, you should give me 5 extra minutes. Okay.
All right.
Okay.
Go ahead.
Okay. So let's get a more fine-grained picture of what this quantum state is. So far, I only talked about the stress tensor. Okay. Let me see what I want to say. Where is it? Okay. The state, the quantum state of the matter here is sometimes called a semi-classical state. Sometimes called a semi-classical Hartle-Hawking state, because it's the way we're going to think about this ultimately is that you have quantum matter propagating on a fixed classical background. So that's where the semi-classical comes from. And we're going to employ, again, a series of conformal anomaly tricks to deduce what the state is. The idea is that, so this here is what we're starting with. We have some stress tensor profile in the bath and a stress tensor profile in the bulk, which is 0. And what we need to do, we need to find, the motivation will be clear in a second, we need to find a coordinate transformation, W as a function of Y, that satisfies 2 conditions. The first is that the stress energy in this new coordinate system, in the flat metric, is equal to 0. Second, that the coordinate system W or W plus minus covers the entire space-time. Okay, and it turns out that the following coordinate transformation does the job. Okay, and the stress tensor vanishes in this state, the 1-point function of the stress tensor. You can convince yourself that there's only one state for which this is true in the CFT, and that's the vacuum state. So in the W frame, I'm going to use that language. The W frame, you simply have the vacuum. Okay, so we did some coordinates. So we had some complicated state here, some state here, and we found a coordinate system where the state is very simple. It's just a vacuum. The next thing I'm going to do is I'm going to express this state in terms of left and right boost energy eigenstates, or basis of those. So maybe I should go back a slide first. There's the boost here, just something like this. Okay. So I want to write something, I want to express O as just in this basis. But this basis, again, is these are energy eigenstates of the boost generator. The way I'm going to go about this, or the way to do this, is to first define your state using the path integral. The vacuum state can be prepared using the standard Euclidean path integral of a CFD from -infinity up to t equals 0, which is represented by this half disk. Okay. To compute these coefficients, what we need to do is we need to evaluate the path integral subject to this boundary condition that we have on one side. I should write like this. On one side, we have the state E, and on the other side, we have the state E tilde. Now, there's a way of interpreting this path integral, not as going from the bottom to the top as we did above here, but you can interpret it as via a evolution using a different slicing. The slicing that goes from this half into the past, the Euclidean past, up to the other half. So we're evolving in this direction. When written in this way, you can think of this coefficient as, you can think of it as the transition amplitude E y e to the minus beta over 2h. H is the boost generator. E tilde y. Since these energy eigenstates are these E's here, these states are energy eigenstates of this H. This is just equal to e to the minus beta over 2e times the delta function e tilde, which means that this state here, we can write it as sum over e to the minus beta over 2e, e left, e right. This is the famous thermal field double state that some of you might have heard about. In the case where you have, a free CFT, this state breaks up into thermal field doubles per mode. So omega here are like frequencies, and n here corresponds to the occupation number. So you have Boltzmann weighted superposition of these states. So the picture in flat space for a free CFD is that you have particles that just propagate this way. Well, waves really, plane waves propagating this way, and they're entangled across this horizon and this horizon. This is the famous Rindler decomposition of the vacuum into left moving and right moving entangled pairs across the Rindler horizon. And this is like this. This is the origin of the Hawking radiation for this model. It just so happens that the Hawking radiation is quite literally is Rindler radiation. And so what this is describing is that you have a black hole which is emitting Hawking radiation, but it's also absorbing Hawking radiation, or rather absorbing radiation coming in from the bath region. I'll take questions on this in a second. Let me just first summarize. Well, a comment, then a summary, that that the path integral that I considered on the previous slide had the CFT on flat space on the entire lower half plane. But to get the actual physical quote unquote semi-classical state, the CFT path integral, it runs over flat space for some period, and then it transitions to ADS2 in this region. So it's this hybrid CFT path integral where the metric is flat in one region and then ADS2 in another region. And the claim is that, I mean, this is a slight complication, but it doesn't really change the physics. You still get these entangled particles across the two horizons that I described on the previous slide. So to summarize, what we did in this lecture is, well, we considered JT gravity coupled to these external baths, and we constructed an eternal black hole inside of ADS that's in thermal equilibrium with incoming radiation from an external bath. And next time, well, I'll review this, but also I'll tell you why everything I told you so far is a lie. All right, now let me take questions.
Great, thank you. All right, Stefano.
I wanted to ask a clarification. I'm a little confused by the different vacuum here. So in a few slides ago, you said that the CFT is in the vacuum in the bulk, but it's not in the vacuum in the path. So I was thinking there, maybe you can interpret that as a just like in Hawking radiation, some asymptotic observer and enfolding observer that sees a vacuum, and asymptotic observer sees Hawking radiation, and that asymptotic observer would be some person in the path. But in this case, where you have now you wrote down a vacuum in the W vacuum, and then you actually see Hawking radiation, seems to me from this last picture, in the bulk as well. So how do those two things connect to each other?
Good. So the first statement is that even after drawing this and so on, the stress tensor in the bulk is still equal to 0. So it still looks, I think this means that an infalling observer in the bulk will not actually see the Hawking radiation. But the stress tensor in the bath is not equal to 0. So again, I had a lot of stress tensors in my talk, but the physical ones are those two.
Excuse me, that expectation value of the bulk in which vacuum is computed? In the W vacuum or in a different vacuum? Because like, aren't those states that you wrote down, E left and E right, aren't those bulk states? So isn't the bulk state the entangled state of E left and of ingoing and outgoing modes?
I mean in this state. So this path integral here defines some state. And the claim is that in this state, the stress tensor is equal to, the stress tensor in the bulk is equal to 0. Actually, maybe let me see. What's I think we should. Okay, to talk about the stress tensor, let's go back and not talk about the quantum state. Let's go back to this discussion. Is that okay? So the stress tensor here is 0 in the bulk, independent of which coordinate system you use. Because remember, the eternal black hole is a vacuum solution. And I want to interpret this as saying that an infalling observer, if they're inside the ADS2 region, they actually don't see the Hawking radiation if they're just freely infalling. But if they're in the bath region, they will see it. I agree that this is weird, but I think this weird aspect is just due to the simplicity of the model. In particular, I think I know of a correction. I know of a way to fix this model to make the experience of the infalling observer more uniform. I think you need to couple the matter to the dilettante. That's my suspicion.
Okay, I think this is clear to me. I think this last thing you said clarified this slide. I think a little confused by that picture that you have in the next slide, where you have infalling and outgoing modes apparently from a bool point of view, but like, are those modes actually occupied? No, sorry, the one after that. Yes. Are those left and right modes actually occupied when seen from an observer? Where exactly? In the bath?
Good. Okay, let me try to explain it in the following way. So, yeah, so here the relation, okay, good. They're occupied, or rather these modes are the relation here between W and Y is W in the flat metric and Y also in the flat metric. But remember that we said that Y in the flat metric has a non-zero stress tensor. So an infalling observer, well, and if we completely ignore ADS2, if we're just literally just thinking about this system here. Wait, I'm confused now. I think I managed to confuse myself. Okay, let me fall back into the usual answer given. All I'm doing here is I'm considering the Minkowski vacuum, and I'm choosing to split it in terms of Rindler modes. An observer that's just freely falling in, or just freely traveling in Minkowski, they will see nothing. But if they start to accelerate, they will see these modes. But these modes are occupied irrespective of whether the person chooses to accelerate or not.
Picture is perfecting for the path.
So can you say that again?
Is it basically just a row effect for the path, and so ADS2 here doesn't matter? Is that the idea here? So this you wrote down is just considered from a path point of view, and just have Hawking radiation coming out of the horizon from a path point of view.
Yeah, you can think of it like that.
Okay.
Yeah.
But you could also think of it as a like undergo radiation for accelerating observer.
Yes, you can. Well, I think that's essentially what Stefano, I think. Well,
okay.
Yeah, but okay. Yes and no. So I would say that an inertial observer in the bath will see these modes. However, you need an accelerating observer in the bulk to see the modes.
Right. Okay. Good. Okay, Christian.
So my question is about, I guess, your first slide where you're talking about the central dogma. So in that picture, you basically say that if you're just observing the black hole from the outside, you can sort of choose some, I guess, cutoff surface somewhere close to the black hole, I guess, which is you give by its blue line, and then you replace everything inside of it by some unitary quantum system, and then everything else outside, I guess you could view as this bath that you're coupling it to. I mean, if I just do this naively, let's say for an asymptotically flat black hole, I just choose some surface at some constant r, and then associate some sort of, I guess, some Israel junction condition for this surface. there would be some sort of discontinuity. I would think there would be some kind of discontinuity in the stress tensor by introducing this sort of surface.
I'm not sure what's causing the discontinuity. Here we're just imagining that there's, well, in the asymptotically flat case, this statement is not super precise. Let me first emphasize where the statement is the most precise. The most precise is where this blue dotted circle is like the ADS boundary. Okay. For a black hole in asymptotically flat space, I want to say maybe something like, you imagine you have an imaginary surface around the black hole, and then you, if you're outside that imaginary surface, and somebody had swapped the black hole with another object of the same mass, well, gravitationally, you wouldn't know the difference. And the claim here is that this other thing could be a quantum system, and you also would not be able to tell the difference even if you do some more careful measurements on the Hawking radiation and so on and so forth.
Okay, I guess my motivation for that was like the surface that you define. I mean, you should expect, I mean, from ADS CFT, you should expect that this quantum system that's inside of this cutoff surface, it's holographic in some sense.
I would say it depends where the quantum surface, where did you place the quantum system? Let me give you an example where what you said was, the answer to what you said is yes. That's where the blue surface is the ADS boundary, and you've replaced, and you are replacing the entire bulk by the holographic dual on the boundary. Is that what you meant?
Yeah, but I also maybe mean like maybe some sort of some coarse grained version of it in the sense of like holographic renormalization. Where you could move the boundary closer to the horizon as you coarse grain the degrees of freedom.
Yes, exactly. Yes, I think I agree with you now. Yes, thank you.
Thank you.
Okay, Ahmed.
Yeah, I have a question about this Euclidean gravity sorcery.
Okay.
No, just a question actually. So, if you don't know about statistical mechanics, but you do ordinary thermodynamics, if you know the heat capacity or something, I think if you integrate the heat capacity over temperature, something I can't remember exactly what, then you will get the entropy of the system up to like a 0-point entropy. So in some sense, just doing thermodynamics, you can actually get the entropy from macroscopic observables. So in what sense is the sorcery of Euclidean gravity like more scary than the wizardry of thermodynamics?
Good. So what you're saying is that if I give you, like, let's say, the energy as a function of temperature, then I can derive S. I can derive the thermal entropy. The difference is here you're not just given the energy. Here you're given the gravitational configuration that gives you this S. Like you're computing your we started out by trying to evaluate trace e to the beta h, and that's and then you find that only, well, I feel like I'm just going to repeat myself, but it's just it's one configuration that gives you that number.
I would say it's more because you need to vary the temperature, right? Or can you do it without even varying the temperature?
to get the formula, you do need to vary the temperature, but even when you vary the temperature, you don't see all the e to the s many states, right? Let me see.
I guess one thing that is different is that we seem to get a 0-point entropy, I guess, that at least. I don't know if that's significant.
Yeah, so I guess in this case, we do also get the 0. Here's the 0-point entropy. So yeah, so I agree that that's one difference. Yeah, but I'm that your resolution feels like a cheat to me for some reason.
Okay. Thank you.
Mm-hmm.
All right. Any other recordable questions? Okay, so if not, let's thank Ahmed again, and we can stop the